So for my topic of rolling circles, I'm going to be going through how we find the points of a locus. So in this case, I'm going to be using a cycloid to demonstrate, but the method is pretty much the same for any other type of rolling circle. So maybe an epicycloid or anything like that. The method stays pretty much the same. So as long as we get this one down, the rest will follow suit. So for this question, it says construct the path of a locus that follows point P. Point P is down here. As the circle rolls clockwise, so clockwise meaning it rolls around to the right, so it's going to be rolling around this way without slipping. And without slipping means that the circle does not move from that fixed line, doesn't go up or jump or bounce or anything like that, stays on that line. So if you imagine a car driving down a road, there's no potholes, there's no bumps, nothing like that, there's no speeding, and the wheel always stays on the road. And finally, for half a revolution. So for half a revolution, of the circle is what that's referring to. So I have my circle already divided out into 12 equal parts. So I don't need to go the last 6, just the first 6 parts, because it's half a revolution. So usually you'd be given just a line in the circle, but I've just gone ahead just to make the video a little bit quicker, and I've divided up our line just using a 30 degree and a 60 degree set square into, we only need the 6 parts, but I divided it into 12, and I did the same thing for here. So we can imagine from point P out to 6, that length there is the circumference of this of half this circle here. So if we were to grab the top of that line and pull it down like an involute, that would be the exact same length as that there. So that's the half the circumference of the circle. And then from that we have marked out our centre point as well, because as the circle rotates, the centre point will always remain in the same spot. So that's just setting up the question. Just as far as teaching this topic, one of the tricky things would be for students to actually visualise what's going on here. So what's going to be happening is I'm going to be rotating this circle along this line. So the first one, if you can see point 1 there, that's going to link up with 1 on our line here. So we have to imagine in our heads that that's going to rotate like that, and that can be tricky for a lot of people, not just students but myself as well. So a little thing I did was just make up a small little template. I did it 2 minutes there before the video, and have the same size, everything's the same as on the page. So if I just line that up with all the points in our lines, straight away we can just, if I rotate that onto 1, make sure all the lines, the axis is lined up and lined up with our points, straight away we can actually just see where point P is going to be. So if students are finding it tricky, a little thing like that can help. So we know it's going to be around there somewhere, and if you go on to 2, same thing, your point's going to be here, 3, 4, etc, etc. So it's just that's a nice little tool, just a resource just to have, just to be checking if it just, when students are introduced to the topic, it can be a little tricky. So we're going to start off the question. I'm just going to run through a few of them, just how we go about doing it. So the first thing we're going to find is the centre point when it's at, we're going to find P when the circle is at the centre point 1. So what we're going to do is take a measurement on the original circle from the centre point to P, and we're going to put the point of our compass on C1, and we knew from the template there that's around this way somewhere, so we're going to strike an arc. Strike an arc there. And then the next thing we need to find is where 1 is going to be. So we need to find the distance from point 1 on the circumference of our circle to point P, and then we bring our point down to point 1 that we have drawn out here, and we strike an arc. Now where those 2 points intersect, that is a point on our locus. So we're going to do the same thing again for our second point. Find the distance from centre point to P, and we're going to 2 this time. Strike an arc again, so we know it's going to be around here somewhere. Then we're going to need from 2, so point 2 to the point 2 on our line, strike an arc. That's our second point. Do 3. I'll go up to point 4 just to make sure we have it. Go to 3, out to point P, 3 on our line. So intersecting lines where they intersect, that's another point. And we'll do the fourth one just to be sure. Point P. And go to 4, down to P. And bring it over to 4 on the line. And where that's the line intersects, like all the other ones have done, is the point in our locus. So if I were to just sketch that out, I've got another colour, just so you can see. And I start from P and go through all our points. That there is the start of our cycle. So if I was to continue on, it would keep going to about halfway, and that type of a rolling circle, that type of a locus, is called a cycloid, because it moves along a fixed straight line. There's no curve that's on a cycloid. So while I have that, I'm going to show you what triangulation is. So if I was to, I'll use point 3 here. So if I was to imagine the circle is after moving over to point 3. So if we use our template, our circle is after rotating the whole way over to 3. So our circle is going to be here now. So we can imagine that circle is gone. It's now in this position. I'll just draw that in just to show. And as you can see there, the point that we found earlier for 3 is on that circle. And there's our centre point. So if I was to get my set square and go from my centre point to the point on the locus, bring it 90 degrees down, which I already have, and if I join the point to that new point down there, we have a triangle. And this is called triangulation. This is how we find all of our points. I'll do the same thing for point 4, and we can see that we'll have another triangle. So we say that we pretend that the circle had to roll on again to point 4, and this time our point that's on the locus is also on the circle, is out here, so we join that line again. We go 90 degrees back down to our fixed line, and we join those lines again. We have a triangle. And see how the triangle is changing shape. So it's a 90 degree right angle triangle there, then it changes again, and the whole way for every single circle a triangle can be found, and that's the method that we use to find these points, triangulation. So that's my video, just to show how we find the points. I hope it's clear and we're able to learn from it.